How could the Japanese, perceived by many Americans as technologically inferior, have produced such an exceptional fighting machine? This dismissive attitude would soon change, and the story of how American scientists and engineers unraveled the mysteries of the Zero's power plant reveals one of the most fascinating technical detective stories of World War II. In the early months of the Pacific War, American pilots flying P-40 Warhawks and F-4F Wildcats found themselves consistently outmatched by the nimble Zero. The Japanese fighter could climb faster, turn tighter, and fly farther than anything in the American arsenal. Allied pilots who survived encounters with Zeros reported that the Japanese aircraft seemed to defy the laws of physics, executing maneuvers that should have been impossible. These reports created an almost mythical aura around the Zero, enhancing the psychological advantage already enjoyed by Japanese forces in the wake of Pearl Harbor. The Zero's dominance was so complete that it threatened to give Japan uncontested control of the Pacific skies. For American military planners, understanding this aircraft became an urgent priority. But there was a problem. They had no Zero to study. The Japanese military had taken extraordinary precautions to prevent their advanced fighter from falling into enemy hands. Pilots were under strict orders to ensure their aircraft were completely destroyed if forced down in enemy territory. For months, the Zero remained an enigma, known only by its silhouette and the deadly effectiveness it displayed in combat. The breakthrough came in June 1942, following a significant moment in the Pacific War. During the Japanese attack on Dutch Harbor in the Aleutian Islands of Alaska, a Zero piloted by Flight Petty Officer Tadayoshi Koga was struck by ground fire. With his aircraft damaged and losing fuel, Koga attempted an emergency landing on what appeared to be a suitable field on Akutan Island, about 25 miles from Dutch Harbor. What he didn't realize was that the seemingly solid ground was actually soft marsh. When the Zero's wheels touched down, they dug into the boggy terrain, causing the aircraft to flip over. The impact proved fatal for Koga, but his aircraft remained largely intact, a priceless gift to American intelligence. For nearly a month, the crashed Zero lay undiscovered in the remote Alaskan wilderness. It wasn't until July 10th that a U.S. Navy patrol plane spotted the distinctive silhouette of the overturned fighter. A recovery team was dispatched immediately, and they found what military intelligence officers had been desperately seeking, a nearly intact A-6M Zero, the first to fall into Allied hands. The aircraft was carefully extracted from the marsh, crated, and shipped to North Island Naval Air Station in San Diego, California. There, a team of engineers, metallurgists, and aeronautical experts waited eagerly to begin what would become one of the most important technical analyses of the war. The Zero was meticulously disassembled, with each component cataloged and studied. Every aspect of the aircraft underwent scrutiny, but it was the Nakajima Sakai 12 engine that perhaps held the most surprises and revealed the true nature of Japan's engineering prowess. As American engineers began their examination of the Zero's power plant, they were initially puzzled. The engine didn't seem particularly advanced. In fact, by American standards of the time, it appeared somewhat conventional, a 14-cylinder, air-cooled radial engine that produced about 1,000 horsepower. This was actually less powerful than contemporary American engines. The Pratt & Whitney R-1830, used in American fighters like the F-4F Wildcat, for instance, could produce up to 100 horsepower. If the engine wasn't exceptionally powerful, how did the Zero achieve its remarkable performance? The answer began to emerge as the scientists delved deeper into their analysis. The secret wasn't in revolutionary technology, but in Japanese engineering philosophy. The Nakajima Sakai engine represented a different set of priorities and trade-offs than its American counterparts. The first revelation came when they weighed the engine. The Sakae was significantly lighter than American radial engines of similar displacement. Through careful design and material selection, Japanese engineers had created an engine that prioritized power-to-weight ratio over durability. Every component had been scrutinized for potential weight savings. Where American engines used heavy castings for durability, the Japanese used lighter materials and thinner walls. The metallurgical analysis yielded further insights. The Sakae engine contained aluminum alloys that were surprisingly sophisticated for the time. These alloys allowed for lighter components without sacrificing too much strength. Additionally, the Japanese had developed precision manufacturing techniques that enabled them to maintain tight tolerances with these lightweight materials. Another surprise came from examining the engine's accessory systems. The Japanese had eliminated or simplified many components that American engineers considered essential. The starter motor was smaller and lighter. The generator was compact. Even the carburetor was a study in minimalist design. These weight-saving measures extended to every aspect of the power plant, revealing a holistic approach to engineering that prioritized aircraft performance above all else. But these discoveries also revealed the Zero's fundamental weakness. The Japanese engineers had achieved the Zero's exceptional performance by sacrificing durability and protection. The engine, like the airframe itself, was vulnerable. There was minimal armor protection. Fuel lines were exposed. Critical systems had no redundancy. The Zero was designed for offensive operations, where its agility and range would keep it safe from enemy fire. In a defensive situation or when surprised, these design compromises could prove fatal. This understanding fundamentally changed American tactics against the Zero. Armed with knowledge about the aircraft's vulnerability to damage, American pilots developed new combat techniques. Rather than trying to outmaneuver the Zero, an impossible task, they would use their aircraft's superior diving speed and structural strength to execute boom and zoom tactics. American fighters would dive on Zeros from higher altitude, make a single firing pass, and then climb away before the Japanese pilot could bring his superior maneuverability to bear. The study of the Zero's engine also influenced American aircraft design philosophy. While American engineers didn't adopt the Japanese approach of sacrificing durability for performance, they began to pay more attention to power-to-weight ratios and aerodynamic efficiency. The lessons learned from the Zero study contributed to the development of later American fighters like the F-6F Hellcat and F-4U Corsair, both of which could match or exceed the Zero in performance while maintaining the armor protection and structural strength that American pilots depended on. Perhaps the most significant lesson from the Zero engine study wasn't technical, but cultural. It shattered the prevailing view that Japanese technology was merely copied from Western designs. The Zero revealed sophisticated engineering and original thinking that demanded respect. American intelligence reports following the Zero analysis explicitly warned against underestimating Japanese technical capabilities. This shift in perspective had implications beyond aircraft design, influencing American approaches to the Pacific War as a whole. The story of the Akutan Zero, as it came to be known, illustrates how technical intelligence could change the course of warfare. Before the recovery of Koga's aircraft, American pilots faced a mysterious adversary with seemingly magical properties. After the detailed analysis, they understood both the strengths and weaknesses of their opponent. Knowledge truly was power. By late 1943, the tide of air combat in the Pacific had turned decisively. New American fighters, combined with improved tactics based on understanding the Zero, had neutralized Japan's early advantage. Furthermore, as the war progressed, the Japanese found themselves unable to update the Zero design significantly or replace it with more advanced models. Japan's limited industrial capacity and dwindling resources meant that many Zeros flying in 1945 were not substantially different from those that had dominated the skies in 1941. Meanwhile, American aircraft continued to improve rapidly, with new models and upgrades appearing regularly. This diverging trajectory reflected the fundamental industrial and resource disparities between the two nations, disparities that would ultimately determine the outcome of the conflict. The transformation of the Zero from unstoppable predator to vulnerable prey represents one of the most dramatic reversals in military aviation history. A fighter that caused terror among Allied pilots in 1942 was, by 1945, often described as a flying lighter due to its propensity to catch fire when hit. This change wasn't primarily due to modifications in the Zero itself, but to the American response, a response informed by the detailed technical analysis that began with the study of Flight Petty Officer Koga's crashed fighter. The engine study revealed another interesting aspect of Japanese wartime production. Despite the sophisticated design of the Sakai engine, many components showed signs of hand-finishing and non-standardized manufacturing processes. This contrasted sharply with American production methods, which emphasized interchangeability and mass production. While Japanese craftsmen could produce excellent individual engines, they couldn't match the scale of American engine manufacturing. This discovery gave American planners confidence that a strategy of attrition would eventually favor the United States, regardless of the quality of individual Japanese aircraft. The saga of the Zero engine study also highlights the critical importance of battlefield intelligence and technical analysis during wartime. Throughout history, capturing enemy equipment has provided valuable insights, but few examples have been as significant as the Akutan Zero. The comprehensive analysis conducted by American scientists and engineers turned the tide in the Pacific Air War and saved countless Allied lives. There's a certain irony in how the Zero's greatest strengths ultimately contributed to its obsolescence. The Japanese design philosophy that created such an exceptional fighter in 1940 left little room for growth or adaptation. The airframe couldn't accommodate significantly more powerful engines without complete redesign. Additional armor or self-sealing fuel tanks would have compromised the performance characteristics that made the Zero special. Japanese engineers found themselves trapped by their own early success, unable to evolve their design to meet changing battlefield conditions. The technical analysis of the Zero revealed that its remarkable range, up to 1,600 miles, unheard of for a fighter of that era, came at the cost of pilot protection. American pilots flew with armor plating behind their seats and self-sealing fuel tanks that could withstand bullet penetrations. Zero pilots had neither. Their aircraft could fly farther, but they were much more vulnerable to even minor damage. American scientists calculated that a single .50 caliber bullet in the right place could cause a catastrophic failure in the Zero's engine or fuel system. This vulnerability became increasingly apparent as American pilots learned to exploit it. Naval aviator Jimmy Thach developed the famous Thach weave tactic specifically to counter the Zero's superior maneuverability. By flying in pairs and executing a weaving pattern, American pilots could ensure that any Zero pursuing one aircraft would eventually face defensive fire from the pilot's wingman. This tactic, developed based on understanding the Zero's capabilities and limitations, neutralized much of the Japanese fighter's advantage. The study of the Nakajima Sakai engine also provided insights into Japan's strategic situation. Analysis of the materials used in the engine revealed that Japanese engineers had designed it to function with lower-grade fuels than those used in American aircraft. This suggested an awareness of potential fuel supply limitations, a prescient concern given the oil embargoes that had helped precipitate Japan's decision to go to war and the eventual submarine blockade that would strangle Japan's access to raw materials. The Zero engine study coincided with the pivotal Battle of Midway in June 1942, where American forces achieved a decisive victory that marked the turning point of the Pacific War. While the technical analysis hadn't yet influenced American tactics at Midway, the battle demonstrated another vulnerability of Japanese naval aviation: the limited number of skilled pilots and the inability to replace losses quickly. The American system emphasized pilot training and rotation, ensuring a steady supply of competent aviators. Japan, by contrast, began the war with an elite but small cadre of superbly trained pilots. As these veterans were lost to combat or fatigue, their replacements lacked the same level of skill and experience. The detailed understanding of the Zero gained from the Akuten specimen had profound effects on pilot training. New American aviators were thoroughly briefed on the Zero's capabilities and weaknesses before entering combat. Training programs were adjusted to emphasize tactics that would work against the Japanese fighter. This knowledge helped rookie pilots survive their initial encounters, a critical advantage given the learning curve of aerial combat. By 1944, American technical superiority had become overwhelming. The introduction of the F-6F Hellcat, specifically designed to counter the Zero based partly on knowledge gained from the Akuten examination, gave American carriers a fighter that could outperform the Zero in almost every respect. The F-4U Corsair, though initially considered unsuitable for carrier operations, proved devastatingly effective from land bases, and eventually from carrier decks as well. These aircraft, combined with better trained pilots and superior tactics, reduced the once feared Zero to near obsolescence. The Japanese were not unaware of these developments. They attempted to introduce improved fighters like the Kawanishi N-1K George and the Nakajima Ki-84 Frank, both of which were potentially superior to late-model American fighters. However, by the time these aircraft entered service, Japan lacked the fuel, trained pilots, and industrial capacity to produce them in sufficient numbers to affect the outcome of the air war. The study of the Zero engine also influenced post-war aviation development. The emphasis on power-to-weight ratio and aerodynamic efficiency that characterized the Zero became standard considerations in fighter design worldwide. The lessons learned from analyzing Japanese engineering approaches contributed to the development of American aircraft in the jet age, where weight reduction and aerodynamic refinement were paramount concerns. For the engineers and scientists who participated in the Zero analysis, the experience represented a professional turning point. Many would go on to distinguished careers in aviation and aerospace, carrying with them the lessons learned from their wartime work. The methodical approach to technical intelligence they pioneered became standard practice in military analysis. The story of the Akuten Zero and the subsequent technical analysis represents more than just a wartime intelligence coup. It demonstrates how understanding an adversary's technology can provide insights into their broader strategic situation, cultural values, and industrial capabilities. The American scientists who dismantled the Nakajima Sakai engine weren't just learning about aircraft performance, they were gaining a window into Japanese society and war-making potential. As the war progressed and more Zero fighters were captured or salvaged, the initial findings from the Akuten specimen were confirmed and expanded upon. Additional testing, including flight evaluations of repaired captured aircraft, provided even more detailed information about performance characteristics. American test pilots who flew the Zero gained enormous respect for its handling qualities while confirming its vulnerabilities. One of these test pilots, Marine Corps Captain Robert Baird, remarked after flying a captured Zero, "It was like dancing with a champion. The Zero would follow your lead perfectly, responding to the lightest touch. But dance too roughly, push it too hard, and you'd feel the fragility beneath the grace." This poetic description captured the essential character of the Zero, a masterpiece of finesse and agility that sacrificed durability for performance. The American approach, by contrast, tended toward robust, powerful designs that could absorb damage and still bring their pilots home. These differing philosophies reflected broader cultural values and strategic considerations. By the war's final months, American technical superiority was so complete that the desperate Japanese resorted to using Zeros and other aircraft for deliberate collisions with American ships, the infamous kamikaze attacks. These missions represented the final perversion of the Zero's design ethos. An aircraft created for precision and maneuverability was reduced to a crude guided missile, its sophisticated engineering rendered irrelevant by strategic desperation. The legacy of the zero-engine study extended far beyond World War II. The methodical analysis of enemy technology became a standard practice in military intelligence, reaching its zenith during the Cold War, when both superpowers devoted enormous resources to understanding each other's weapon systems. The approach pioneered by those engineers in San Diego, who carefully disassembled Petty Officer Koga's engine, created a template for technical intelligence that remains relevant today. For historians and engineers alike, the story of the Zero and its engine represents a case study in how technical design choices reflect broader strategic circumstances. The Japanese created the Zero to meet specific operational requirements, primarily the need to project power over the vast distances of the Pacific. They accepted compromises in protection and durability because their strategic doctrine emphasized offensive operations and pilot skill over attrition warfare. These choices made perfect sense given Japan's initial strategy of achieving quick victories through surprise and superior mobility. They became liabilities when the war shifted to a prolonged struggle against an opponent with vastly greater industrial capacity and material resources. The Zero was designed for a short, decisive war. When faced with a long war of attrition, its weaknesses became increasingly problematic. American scientists and engineers recognized this fundamental mismatch between the Zero's design and Japan's strategic reality. Their analysis helped confirm what military planners had already begun to suspect, that Japan could be defeated through a strategy that capitalized on American industrial strength and material advantages. The Zero, for all its brilliant engineering, represented a tactical solution to a strategic problem that Japan ultimately could not solve. The study of the Zero engine also influenced American industrial practices. The Japanese attention to weight reduction and material efficiency impressed American engineers, who incorporated similar considerations into their own designs while maintaining their emphasis on durability and protection. This balanced approach characterized American fighter design through the remainder of the piston engine era and into the early jet age. Today, the Nakajima Sakai engine and the Zero fighter have taken their places in aviation history as examples of brilliant engineering within constraints. Modern analysts recognize that the Zero wasn't simply a copy of Western designs, but a unique solution to specific operational requirements. The aircraft represented a distinct engineering philosophy that emphasized certain characteristics at the expense of others, a set of trade-offs that initially provided advantage but ultimately proved unsustainable in a prolonged conflict. For those American scientists who first examined the Zero's engine in 1942, the experience challenged preconceptions and expanded their understanding of engineering possibilities. It demonstrated that technical innovation could emerge from unexpected sources, and that different cultural approaches could produce novel solutions to common problems. This lesson, that diversity of thought leads to innovation, may be the most enduring legacy of the Zero engine study. The story of the American analysis of the Zero's engine reminds us that warfare is not merely a clash of weapons, but a competition between systems: industrial, educational, cultural, and technological. The side that better understands both its own capabilities and those of its adversary gains a crucial advantage. In the case of the Pacific War, American technical intelligence provided insights that helped transform a desperate defensive struggle into an eventually unstoppable offensive. As we reflect on this historical episode, we can appreciate the dedication of those unnamed engineers and scientists who meticulously disassembled, measured, tested, and analyzed the Zero's components. Their work, conducted far from the front lines, contributed significantly to Allied victory. It stands as a testament to the importance of technical expertise in modern warfare and the power of knowledge to change the course of history. The legacy of understanding the Zero's engine lives on in modern fighter design, where the balance between performance, protection, and sustainability remains a central consideration. Today's aircraft designers still navigate the same fundamental trade-offs that faced their predecessors, albeit with vastly more advanced technologies at their disposal. The lessons learned from studying the Nakajima Sakai engine echo in the engineering decisions made for contemporary combat aircraft. In the final analysis, the study of the Zero's engine revealed a truth that extends beyond aviation technology, that understanding your adversary is the first step toward overcoming them. The American scientists who unraveled the mysteries of the Zero's power plant didn't just learn about an engine. They gained insight into Japanese industrial capacity, strategic thinking, and cultural values. This comprehensive understanding contributed to the development of a winning strategy that led ultimately to Allied victory in the Pacific and the dawn of the American century. The Pacific skies of 1941 were dominated by an aircraft that seemed almost supernatural in its capabilities. The Japanese A6M-0 fighter plane possessed a combination of range, maneuverability, and speed that left Allied pilots in disbelief. When reports first reached American military headquarters about this remarkable aircraft, many officials dismissed them as exaggerations or the product of battle-shocked minds.